Okay, hello everybody, this is Dr. Hassan again in electrical and electronic circuit analysis. In module 3, which is diode related to diode and transistor circuit analysis, we've completed the diode and we started with the transistor. Now I would like to discuss with you the DC bipolar junction transistor bias. DC biasing. So we are going to discuss DC biasing, exact analysis, approximate analysis, these two methods, and then we design BJT circuit as an amplifier. Now, first of all, let me remind you with the principle, let me say, formula used before. First of all, usually we expect that the transistor to be conducting the electrical current to be having BJT junction forward bias and BC bipolar base collector junction reverse bias. Also, it's worth mentioning that the transistor used today mainly manufactured from silicon, and the voltage drop is around 0.7 volt. And also, I would like to remind you with the equation relating emitter current with collector current is beta plus 1 I collector, and I collector is beta IB. Here this is IB, which is a small current amplified using beta to give I collector. One more issue is in the output characteristics. We know we have input characteristics and output characteristics. Input characteristics is the relation between V base emitter, I base, and the results taken to the output characteristics which represent V collector emitter, I collector. We discussed this before, and you remember the curve it looked like in this way, and we mentioned that this is here saturation region, this is active region, this is cutoff region, active region and saturation region, and usually the transistor works as amplifier in the active region. Now, but in the active region, it's worth mentioning here that here you can see this is let me say the output characteristics for typical transistor, and this is V collector emitter, this is I collector. Now in this point here, this is good point for the transistor to work. When I say good one, it means the environment is effective, is sufficient, it's good for the transistor to work even for a long period of time. There is no pressure or stress on the transistor. This is good Q point, we call it quiescent point. Okay, here the concern of having Q point, operation point for the transistor in a low value here, as example in C, is the nonlinearity occur in the curve and in the operation of the transistor. Never work in the 0, 0 origin. Now, the first type of DC biasing, we call it fixed biasing. We need to number the name of the biasing. Now this is fixed biasing. How we know it is fixed biasing? Because you can see that the transistor connected through two resistance, RB and RC only. You see here the emitter connected to ground, the collector and base, rather than we have two separate supply, we connect them to one supply, which is VCC, and here the capacitor as a filter to separate between DC and AC. Okay, and usually in DC it's open circuit, so no connection here. Okay, and the circuit look like similar to equivalent circuit here. Now if I come to find the input circuit, which is the base circuit, voltage and current, and output circuit, which is the collector voltage and current, then I will say that the voltage applied through RB, then base emitter, then emitter. So Kirchhoff voltage law give me here in this formula. If I rewrite it, I will find that IB equal be V collector VCC minus V base emitter over RB. Very simple equation. And if I have IB, I multiply by beta, I got IC. Now I need IC because in the second circuit, which is the output circuit, you can see the voltage VCC applied through RC. So the voltage here plus the voltage here equal to VCC, as you can see here. And we can find VCE, which is what we are looking for, equal VCC minus ICRC. IC already got it here. Now if we want to find, don't forget V emitter is 0 because it's connected to ground, there is no resistance. So VC equal VC minus V, and since this is 0, it is equal to VC. The same thing for VBE, equal VB minus VE, and VB is 0, so it's equal to VB. Now let's take example. Have a look at this circuit. It is fixed bias, I know, because we have two resistance only, one on the base and one on the collector. He asked me to find IBQ. IBQ, it means I base quiescent point. ICQ, VCEQ, VB, VC, VBC. Okay, now let's take them one by one. The first one is IBQ. It's a procedure we need to follow. IBQ is VCC minus VB over RB, as we mentioned in the previous slide. Everything given to you, as you can see here, the values are given to you, and this is beta, and the voltage here is given to you. V base emitter, if he don't give it to you, you assume it to be 0.7 volts because it's constant. Usually it's constant. Okay. Now I got IB. I substitute and multiply by beta to get ICQ. And VCEQ equal VC RC. Similar to the previous slide, we discussed it. We got V collector emitter. V base emitter equal V base because I emitter is 0. V collector emitter equal to V collector because V emitter is 0. Now V base collector, we have V base, we have V collector, just subtract. You see it is in minus. What this mean? This means that the transistor is working, because we mentioned that V base emitter should be forward bias and V base collector should be reverse bias, so it is in minus, as you can see here. Now next, another example here, we change the values. Okay, you can see the values of resistances has been changed, the beta is changed, but have a look here. We follow the same procedure. We found V base, as you can see here. We found IQ by multiplying I base by beta. We find VCE, we find VBE, we find it's just merit of substitution. The same procedure, values change, but the same procedure. And this is the most easiest, let me say, circuit in the biasing, which is fixed bias circuit. Now saturation occur. Saturation occur when bipolar junction, when base collector, I mean here between these 2 points, okay, is no longer reverse bias. So what happened? VCE will become 0. Saturation is the highest, then the current will follow directly. Okay, and if this happened, similar to the example, two examples just discussed, we can see that here it's supposed to be minus V collector emitter, but because saturation is gone, so the current become the highest. Okay, compare with the normal current without saturation, it was 2.3. The highest current allowed here is 5.45 in saturation situation. This is good, important to know, because if we know the highest current, we can select a suitable transistor to my circuit. The second example discussed also, we repeat the same thing. We assume it's saturation, VC is 0, then we got the current. Compare the current with the normal current. So saturation is higher, the normal is lower, then that means the transistor is working in good environment. Load line analysis discussed in DC in diode and transistor is still valid, and you can use it graphically to find the quiescent point or Q point of operation. And just to remind you that we have this formula which say V collector emitter equal VCC minus ICRC. So if IC is 0, then VCE equal VC, we got point. If VC is 0, then IC equal VCC over RC, we got another point. We make a line between them, and now we go to the input characteristics. We got IBQ. If we know the IBQ, as example, this line will be used, then this is the point of intersection, represent the operating point. Here VCEQ, and here ICQ. You got it? It's also a procedure, but we need to mention something here. What happened if IB change, the base current change? As example, base current was this one, it increase or increase more. What will happen? we can't see that the quiescent point moved from here to here, to the left, but higher, okay, higher level. And this reflect, rather than we have VCEQ here, it become here, or if we increase more IB, it will become here. So this means that increasing the current IB will reduce the VCEQ of the transistor. Take this picture and put it aside. This is one view. Another view, what happens if we change R base, R collector? We change this to become, rather than R1, it become R2, it become R3. You see, we are, let me say, increasing R. We can see that this point will move from up down, okay, and based on this, the quiescent point again move to the left, linearly, almost linearly, and VCEQ will move also to the left, mean get reduced. This is another also point, or let me say picture, we need to put it aside, okay. One more picture is when VCC change, it means VCC 1 here, okay, VCC 2, VCC, we change it, okay, and we can see that what happen is when VCC get reduced, this point will move, and this point will move, the whole line will move to the left. Again, the quiescent point will move. Now, let me summarize these three pictures. When we change the resistance, when we change the VC, when IB, when we change the VCC, what happened? The quiescent point moved. If quiescent point moved based on some change occurred in the parameters of the circuit and may have operating point for the transistor in a wrong place, and this is not acceptable. This is not good for the stability of the transistor operation. Maybe the transistor will work in overloaded place or a linear place, which is not desirable. As I mentioned, we prefer that our Q point working in the middle of the active region. Okay, let's take example and we will clarify this point through this example. Given the load line shown in figure and define Q point, determine the required value VCE. As usual, he asked about the output voltage VCE, RC, RB for the fixed bias, and he gave me here quiescent point, you see here. Now I can see that this is VCC and this is VCC over R. If I have VCC and have current, I can find RC also, okay, and the operating point is clear for me. Now the solution is VCC from the graph, we got it, okay, and IC from the graph, we got it, then we can find RC. Both of them, we got them from the graph. Then we go to find IB, okay. IB is VCC minus V base emitter, which is 0.7, okay, over RB. Then we have this, we have this, we have this. Let's get RB. We got it, okay. Another example here. Determine Q point for this figure. Also find the new value of Q point if beta change. Now here beta given 100. What is the value when beta become 150? Now let me take the two steps. First, when beta is 100, as usual the same procedure, IB VB VCC minus V base over R base. We got it, multiply by beta, we got I collector, we multiply by RC and subtract from VCE, we got the voltage. So this is the Q point, this is the Q point as you can see here, and this is the voltage, and this is the current IC, VCE, IC, okay. I repeat the same thing but I change beta, and this is what I got. If you compare between voltage here in the first situation and second situation and current here and here, we can see it is changed. It means the operating point changed. This means that when we change beta, it means we improve the amplifying, increase the amplifying, rather than it's 100 times, it become 150. V collector emitter and I collector has been changed, which is not good for the stability of the circuit. So this tells me that fixed bias configuration is not stable. It's not stable because the point, quiescent point is moving. Can we fix this? Yeah, we can make some improvement in the circuit to fix it. I will start with the first improvement, which is the other circuit, which is called emitter bias. Emitter bias. What I will do, the same previous circuit, I will add resistance on the emitter. Okay? When I add resistance on the emitter, it becomes 3 resistance circuit because we have RC, RB, and RE. Okay? This will improve the stability level of the fixed bias and become more stable. Now, as usual, we start with input circuit, which is on the base here, and then we go to the collector circuit, which is here. So input circuit, now we have R base, V base emitter, similar to the fixed, but we have another resistance, which is RE. So rather than only 2 voltage, the Kirchhoff voltage law will be VCC, IB, RB, VB, and we have also voltage drop across emitter resistance. So a little bit happened in the improvement of the equation for fixed bias. As you can see, this is the fixed bias only. But now in the denominator we have beta plus 1 RE, because as you know, I need to substitute here I emitter by beta plus 1 I base from principles, and simplify, we got this equation. A little bit get improved. As you can see here, VC here is this voltage minus drop here. So we substituted, we have everything, we got VC. VE is VC minus VCE. We have VCE, we already got it here, as you can see. VC, we got it here. Just substitute, we got V emitter. Or we can find I emitter, because I collector is similar to I emitter, it's the same. So R emitter by I collector give me the same voltage. V base is V base emitter plus V emitter, as we discussed before. Okay, we have these 2 voltages, we got it. And V base collector, V base minus V collector, we have this value, this value. Just substitute. Again, it is a negative, which means it is reverse bias. The transistor is in forward bias. Also, the saturation could occur. So in this way, as you see, the equation reduced to VCC minus, there's no VCE. VCE becomes 0 over RC plus RE. Now, if you apply to this idea to the previous example, okay, you can see that the current we got is 6.67, okay, which is around 3 times this value. Okay. Now, if we work using load line analysis, we can do the same. We can find also the operating point, and then we can go to calculate V collector, V base, V emitter, all of them. Because from the open circuit, from the load line analysis, we will find the quiescent point. It means VCE, rather than by calculation, we will find it from the graph, and IC. Definitely Q here. Okay? So the procedure is clear. We can apply it and also graphically found the unknowns of the circuit. Now let me compare. Now it seemed to be that when beta was 50 for the previous circuit and become 100, I base increase, there is change, okay? And the same thing for collector, and the same thing for V collector emitter. There is differences, but it's still somehow acceptable, okay? What we will do, we will make another improvement in the circuit to have a new circuit called voltage divider bias. Here, I added another resistance between base and ground in parallel with the RE. Now this circuit called voltage divider bias. Just a minute, let me summarize. We have fixed bias, we have, which is 2 resistance circuit. We have emitter bias, which is 3 resistance circuit. We have voltage divider bias, which is 4 resistance circuit. Now, how we let me say solve or analyze the circuit. We have 2 methods. One of them is the exact method, and the second name is the approximate method. I think the name is clear. What is the meaning of exact and approximate? We will discuss them. Have a look. Now, exact circuit. In exact circuit, we analyze analytically. This is the input circuit. Okay, as you can see here, this is the base circuit. Now, R1 and R2 are connected in parallel. As you can are connected in this way. the supply apply to R1 and then it go to R2 and RA, they are in